Hello everyone. In this video we are going to start talking about calculus. Now calculus is the math of change. So any type of change that you can think of is calculus in one way or another. So calculus is actually used every day in multiple different forms and jobs to make the real world applicable. Everything from electricity to chemical reactions to how your pool boy fixes the chemicals in your pool. I mean, it applies to many, many different things. So, uh, we are going to start with a basic one to help learn all the different definitions and symbols that we have to know for our calculus stuff, and that is slope. So in college algebra or some such, you probably remember that slope is rise over run, but that's actually not as accurate as you might think. It's true, but really rise is the change in the horizontal distance. So the up and down, the y's, which is where we get y2 minus y1 for the slope formula. And the run is the change in the vertical distance. So the x's, which is where we get x2 minus x1. And that is how we got our slope formula. So this change in y's over change in x's is the best way to describe slope as its definition if we're talking about general terms. Which is all well fine and good as long as we're talking about a straight line. So we can connect 2 points as a straight line perfectly easily and there's no problems. The slope formula works. But most things in real life are not straight. So what if we wanted to find the slope of a curve? Well, if we have a curve, like here, and we have these 2 points, and we draw a straight line between them to find the slope, that's actually not the slope of the curve, is it? It'd be the slope of that straight line. So the closer the points are, so the closer Q gets to P, the closer we get to a tangent line. So these lines here that have 2 points are called secant lines, and the tangent line is the line that only touches the curve at that one point. And since we want the slope of the curve at just a single point, we really want the slope of this tangent line. But using the slope formula that we learned before, we would actually have the slope of the secant line, which isn't accurate. I mean, the closer we get to P, the closer our slope is going to be because the closer our secant line is, but it's still not going to be as accurate as we need. This idea here is called the tangent line problem. And you can look that up on Google under that heading and you will get lots of different things. But we're actually going to talk about the tangent line problem in another section. This is just to get us started with the idea of how it works. Because what calculus is, the math of change, to be able to do the math of change, we need some new definitions and new ways of talking about things. So it really leads us to our next idea. If the only way we currently know to get a slope is with the slope of a secant line, we're going to call this the average slope of the curve. All right? Be the average slope of the curve. And then the slope of the tangent line would give us the instantaneous slope of the curve at that single point. And to be able to talk about this instantaneous slope, we call it a limit. So the limit of the slope as we get closer and closer and closer to A is going to be the slope of the tangent line. So it's a small distinction here, but it's significant enough that we had to come up with some new language for it. And we'll talk more about the differences in the symbols and what they mean in section 2.2. For now, let's talk more about average slope, because here's the thing. It's kind of weird, but most things are actually the slope of something else, because calculus is the math of change and slope is change. So let's take an example here. Let's take this real world example. Jack throws a baseball as hard as he can, and we want to know the average velocity meaning the speed of the object as it travels in a given direction of that ball. So let's draw a picture, because it's always easier to picture things. Alright, so here's we got Jack, and Jack takes a ball and he throws it as hard as he can, and it hits the ground. Okay? So the point in which the ball leaves Jack's hand, our timer starts. So time 0, the ball leaves Jack's hand. And we don't know, but his height is going to be something. We don't know what that is. Alright? We'll just call it A for purposes. When the ball hits the ground, we don't know what time that is, but we do know that the height of it is going to be 0, right? So we'll call the time as B, just for the sake of easiness. So let's figure out the slope of this idea here. So if we have the slope, the average slope of height versus time, so height, where it lands would be my y2, and where it starts would be y1, so y2 minus y1 over x2, and time is always x, so x2 minus x1. So that would give me a slope of negative a over b. So height is feet, right? And time is in seconds. So this means that I have a slope of negative a over b feet per second. Is feet per second a velocity number? Well, yes, it is. So with this idea here, we know that average velocity, let me write this correctly, average velocity would be the slope of height. So this would be the slope of our position function, or it would be the slope of the height function. All right? So velocity is the slope of height. So let's talk about this a little bit more generally. Let's see if we can find us a formula for this. So let's bring back Jack and his lovely baseball. All right. So let's say that we want to go even more generally. So we're not having a start and an end point. We want to know more along the lines of some weird place here that we don't know and some weird place here that we don't know. We don't know the time or the height of either of these locations. Okay? Very general formula. Now we do know that this curve here is the position function. So it's the height of the ball as it travels through the air. So if we have the height here as A, and, excuse me, no, that's time. This is time, my bad. So time at this first location, let's call it A, and time at the second location, we'll call B. That means that the height here would be the position function at time A, and the height of B would be the position function at time B. So if we know that velocity is the average of position, then we can figure out, because we're awesome like this, that the slope of my position function would be the change in y over the change in x, or the change in height over the change in time, same thing. And if you're wondering, this triangle here, this is change. This symbol here means change. And it is also the Greek letter delta, is where we got that. So if we go by y2 minus y1 over x2 minus x1, well, y2 would be the position, so position at time B minus the position at time A over the time B and the time A, which is where we get a formula for the average velocity. So we can use this lovely formula that we just found, and we can figure out our next example here. So we're back to still on Jack. Jack throws a baseball as hard as he can. We know that the position at 3 seconds equals 112 feet, and the position at 6 seconds is 108 feet. So find the average velocity of the ball over the interval of time 3 seconds to 6 seconds. So we can use the formula that we just created to let us do this. So the average velocity would be y2 minus y1. So y2 minus y1 over x2 minus x1. So y2 is 108 and y1 is 112 over 3. So this gives me negative 4/3 feet, because height is feet, over 3 seconds. So that's negative 1.33 feet per second. Which makes sense because as the ball travels through the air, you've got wind resistance slowing it down, as well as gravity slowing it down. So it decreasing in speed makes perfect sense.